Okay, so let's have a look at question 4 of the foundation paper, paper 2. So here we have a magnetic toy.
Water, fire, air, and dirt. In magnets, how do they work? And I don't want to talk to a scientist. Y'all mother lying and getting me pissed.
That uses ring-shaped magnets. So look at figure 6. Here is figure 6. The magnets can move up and down the rod. Ring magnet B appears to float. So this one appears to float. The magnetic poles are labelled on the ring magnet A. Label the magnetic poles on ring magnet B. Well, we've got repulsion going on. This must be being pushed up, which means it must be pushing that down, which means that you must have like poles. So like poles repel. What does that mean? It means if they're the same, they repel. So you must have the North Pole down here and the South Pole up here. Okay, so that's that mark done. What would happen if you turned magnet B upside down? What would happen if I turned this around, which would mean that the South Pole was facing the North Pole? They would attract. Magnet B would be touching A. Okay, so that's enough detail for that. Let's have a look next bit. Here we have a sort of classic arrangement for a demonstration. The circuit is open, so it says we have 4 plotting compasses. 1, 2, 3, 4. The needle of a compass is a magnet, right? So compasses, that's what they are. They're little magnets, and the little needle rotates around freely. Like if you just hung a magnetized nail on a piece of string, it would rotate around freely and end up pointing towards the North Pole. So explain why the compass needles all point in the same direction. Right, so because the circuit is open, whenever you get a current flowing in a wire, it becomes a magnetic. It has an associated magnetic field. So it becomes magnetic, right? That's why you can make solenoids. So you've probably done an experiment where you get a nail, wrap a wire around it. When you turn on the power, when you switch the switch so that current can flow through the coil, the nail picks up paper clips or picks up anything magnetic, any magnetic metals. So as long as the circuit is not closed, as long as the circuit is not a complete circuit, then there'll be no magnetic field from the wire. So the compasses are just pointing towards the North Pole. So that's what we need to say. So the
compasses point north due to the Earth's magnetic field. Right, that should be a capital E. The circuit has no current flowing. 3 dots means therefore no magnetic field. Right, so I've gone overboard and I've really made sure I've explained that clearly.
Next bit, figure 8 shows the switch closed. So we can see the switch is closed now. So now we have a current in the wire. The compass needles all change direction. On figure 8, draw arrowheads on the 3 incomplete compass needles to show their direction. Right.
Plotting compasses show the circular field pattern around the wire.
Now if you notice here, it shows you the direction of the current, right? If current is flowing up, I have a handy rule, it's called the right-hand grip rule. If you point your thumb in the direction of the current, then your fingers will point in the direction of the field. You get a magnetic field going around in a circle like this, right? So we can see one compass has been added on here and it's pointing this way, which follows my pattern. If my thumb's pointing up, my fingers will be the direction of the magnetic field. So they will continue, they will continue round in a circle like this, right? So again, pointing up, you get a magnetic field around in a circle. It sort of follows the same pattern as the thumb with fingers sort of curling around like this, right? Your thumb would represent current. So the right-hand grip rule allows you to make these predictions. Okay, so that's one mark done. Another one. What would happen if you to the direction of the compass needles if the current was reversed. Okay, so again we can look at our example of the thumb here. Okay, flip this over, what happens? Well, if I flip my thumb over, so my thumb's pointing down, this time my fingers will be kind of coming around this way, right? So my thumb's upside down. It's still my right hand thumb, my right hand that I'm doing it with. So the field would
reverse direction. Point in the opposite direction, basically.
Okay, and so now we have figure 9. It shows a coil of wire in a circuit. On figure 9, draw the magnetic field due to the current in the coil. So this is the cool thing is that if you have individual loops of wire like this, right, and the current is flowing down here and up here, if I use my right hand grip rule, then around this, I'll just use a different colour pen, so I'll use this one. Around this loop here, where it's coming up, right, you'd have a field coming around in this direction. Okay, so you'd have loops this way, right, and again the current will be flowing up and down here, up and down here. So where it's flowing up, you get little loops in this direction, and where it's coming back down again, so the thumb would be this way, the loops are this way round. Right? Now, I've drawn this a little bit messy, but I'm going to throw up a picture that shows how when all these things interact with each other, they all add up to make a field that looks just like that of a standard bar magnet, north, south. So if you have a standard bar magnet, you get, let's just move this over. If a standard bar magnet, you get a field that looks like what? A field that looks like it's coming out of the north and going into the south. Right? That's what you should see. Coming out of the north and going into the south. Okay? So you can get that pattern by putting a piece of paper and sprinkling iron filings on top, and you'll see the same kind of pattern. Or you can place little compasses all over the shop, all over the place, and you will find that the compasses always line up with this field. So I simply have to replicate that onto here.
A coil of wire with an electric current flowing through it produces a field similar to that of a bar magnet. But small compasses show up a pattern. Each curved line is a line of magnetic force.
There are 3 marks available. I wonder what all 3 are for. North to south with direction. Again, north to south with direction. Okay, and I'm going to put a few in here. So I'm hoping this will get me all 3 marks. If not, I'll add a section on the end of the video. But usually you would get a mark because you've got the overall pattern correct, which is going from north to south. You've added on direction, so you're showing direction. That's worth probably a mark as well. And also you're showing that at the poles here and here, there's a greater density, or the field lines are closer together, which indicates that's where the magnetic field strength is stronger. So hopefully that will complete that paper. If you've enjoyed this, please like, subscribe, share. Thanks for watching.